In this video, we'll look at reasoning LLMs, which power many of today's most advanced chatbots like GPT-5. We will cover three things. One, what reasoning LLMs are. Two, different inference time and training time techniques to build reasoning LLMs. And three, what the GPT-5 unified system might look like. A short background here. After the success of standard LLMs like GPT-3 and GPT-4, Llama family, and Gemini, between 22 and 24, OpenAI released O1 model in September 24 and framed it as a model that can think. Also, in this article, they are introducing OpenAI O1 as a new series of AI models designed to spend more time thinking before they respond. They also published another article on the same day, and this article is mostly focused on the evaluation, and they are showing that how much improvements they are getting by training this reasoning LLM. If we scroll to the eval part, we will see on different benchmarks, for example, AMI, which contains USA Math Olympiad questions. O1 models are doing significantly better than the non-reasoning equivalent, which was GPT-4o back then. And this line is showing the accuracy of these models. And similarly, they are showing on other benchmarks like competition code, code forces benchmark, or PhD level science questions, O1 is doing a lot better than GPT-4o. After that, we observed a wave of reasoning models from different teams and companies. Popular examples are Claude, Gemini 2.5 Pro, GPT-5, DeepSeek R1, and there are a lot more examples. And most of these reasoning models are released in 25. I think this meme nicely visualizes what we just saw. In 24, we had all these non-reasoning LLMs, and then O1 came. And now we have, in 25, we have a lot more powerful reasoning models being released and introduced. And many of these are doing very good on different benchmarks. So next, let's see what reasoning LLMs are. What is reasoning? If we go to Wikipedia and search for reason, we would see in a great detail what reasoning is, different definitions in cognitive psychology and other domains. We would also see different forms of reasoning. So if you are interested, you can read this page. It's quite long. But the summary is, in cognitive psychology, the definition of reasoning is the process of drawing conclusions based on available information. And reasoning can also appear in different forms. For example, we have common sense reasoning, where questions like, do people wear sunglasses, requires that. We have mathematical reasoning, where the question is just a math problem and then it requires some multi-step reasoning to answer it. We have also other forms of reasoning like multi-hop reasoning, logical reasoning, abductive reasoning, and so on. So this is the definition of reasoning. Now, the next question is, can LLMs reason? And there is a lot of argument between different people whether LLMs can truly reason or not. But what is important is how we define reasoning in LLMs and in AI. And I think a very great definition of reasoning comes from Denny. And Denny is basically founded and lead the reasoning team in Google Brain and now part of Google DeepMind. And in one of his talks, he defines reasoning in LLMs as the presence of intermediate tokens between question and final answer. So, for example, in a non-reasoning setup, we have this LLM, the problem goes here, and then the final answer is out. Whereas in a reasoning LLM, still the problem goes into the LLM, but the LLM first generates some intermediate tokens. And after that, it generates the final answer. So basically, we are going from this quick single pass in non-reasoning LLMs to a sequence of intermediate steps followed by the final answer in reasoning LLMs. Now, to see a concrete example of these intermediate tokens, let's go to Hyperbolic. Hyperbolic is a platform which allows you to use different open source models and run inference, meaning that you send some questions and get some answers. And there are also other providers. I just use Hyperbolic. And then here, there are a bunch of different models we can choose. For example, GPT-OSS is the OpenAI's open weight model. And there are a bunch of other models like Qwen and Kimi K2 and so on. So here, I would first select a non-reasoning model and ask a question like a difficult question like, I just learned AI and it sounds fun. How can I win a Turing Award in 1 year? So now this llama model is non-reasoning, meaning that it may still break down the task into smaller pieces, but it's not really thinking or generating intermediate tokens. So let's see how it responds to this. Winning a Turing award is impressive achievement that requires a deep understanding. And then it started to answer. It's actually giving me a plan, which I don't think is possible. But it's saying month 1 to 3, month 4 to 5, 4 to 6, and so on. And then it stopped here just because I had a limit on the max tokens. But basically, as soon as I asked my question, it started to answer. So this is the final answer of this model. Now, let me use the exact same prompt and switch to a reasoning model like DeepSeek. And I'll keep the same max token, paste the exact same prompt, and let's see what happens now. Now, it's this reasoning here that appeared. If I click on it, it's basically showing all those intermediate tokens that the model is thinking. So it's like, okay, the user just asked how to win a Turing Award. First, the user sounds excited about discovering AI, and looking deeper, they probably don't actually care about the award itself. But so these are basically the internal thinking of the model. And then right after this, when it feels confident to answer, here it started to produce the final answer. And it's basically just going on until it reaches the max tokens. So this is what we refer to as the reasoning models, these intermediate tokens. Sometimes it's visible to the user. In this case, DeepSeek R1 is an open model, so it's visible, the exact thinking process. Some other models, like OpenAI's reasoning models, are not showing the exact reasoning traces. It shows a rewrite of that or a summary of that. But that's about a concrete example. And these reasoning models are better than non-reasoning LLMs. For example, this is a screenshot from a leaderboard, and we see that the highly ranked LLMs are all reasoning LLMs. And the first non-reasoning LLM is ranked 4th. And this screenshot is from a website called El Marena. El Marena is basically a public platform which evaluates different LLMs by pairwise comparisons. And here we are seeing that right now the top LLM is Gemini 2.5, GPT-5 High, and Claude Opus 4.1, and there is a tie, and there are other models. And still, like top 4, top 5 models are all reasoning LLMs. So this shows the power and importance of reasoning LLMs. And in the rest of this video, we will learn different techniques to build reasoning LLMs. So there are lots of different techniques that we can build a reasoning model. And these techniques can be categorized into 2 big buckets: inference-time techniques and training-time techniques. Inference-time techniques refer to those that keep the model unchanged, so the parameters of the original LLM is not touched, and it's the same. So the LLM itself is still non-reasoning. But then we add a bunch of different modules in different ways and different algorithms to make this entire process look like as a reasoning process. So generating intermediate tokens and then the final answer. And we will go over different techniques. But basically, the LLM is not touched. It's the frozen LLM. Training time techniques, on the other hand, they use a training algorithm and some data, reasoning data typically, to continue fine-tuning this non-reasoning LLM. And then the outcome of this is going to be a reasoning LLM. Now, this reasoning LLM knows how to reason internally. So when we want to use it, we can just pass a prompt to it, and then the output would look like a reasoning output, meaning that intermediate tokens followed by an answer. So in this case, when we want to use the model, if it's reasoning LLM, if we use some training time technique to build this reasoning LLM, we no longer need to add additional modules. So with that, let's start with going through different techniques for inference time reasoning models. All right, the first technique is prompting. And the idea of prompting is to use prompt engineering to make LLM generate intermediate tokens. Basically, we are going from this setup, which is a non-reasoning setup, to it's this additional module here called prompt engineering. And basically the prompt first goes into here, and then the output of prompt engineering goes into the LLM. Let's see some examples. For example, we can apply a few-shot chain of thought prompting. And what that means is that, let's say we have this prompt. It's a math question. There are 3 red bags with 5 apples and so on. And then we pass it to this few-shot chain of thought prompting. And few-shot means that we show an example with some intermediate tokens or with some reasoning traces. And then we hope the model to follow the same example. So here, what we see in red is the additional thing that we are including as part of the prompt. And basically what we are having here is that answer 2 times 3 equals 6. So final answer is 6. And then we have now solved this, and this part is the original question. Now, when we pass this to this non-reasoning LLM, this non-reasoning LLM understands this example, and it tries to follow that. So instead of outputting the final answer, it's basically showing all these intermediate steps. And it's trying to follow this exact structure or template. For example, once it reaches the final solution, it uses the exact same format. So, comma, final answer is 6. So here it says, so, comma, final answer is 29. So that's prompt engineering. And this was few-shot COT, meaning that we show one or some examples. We can also do zero-shot COT. We just add, let's think a step by step. And just adding this line allows the model to also think and pushes the model to actually think. So here we see that the model tries to break down the task into smaller intermediate steps and solve them. And there are more prompting techniques, but that's the high-level overview of prompting techniques to make a non-reasoning LLM to reason. The next technique is sequential revision. And here, basically, the idea is to refine the output of LLMs multiple times using the same LLM. So instead of passing the prompt to the LLM and getting the output, we pass the prompt to the LLM. Once the LLM provides the output, we pass the output to the same LLM again with some additional instructions, like evaluate this response and improve it. And then we keep doing this for a fixed number of iterations. And once it's over, we can pick the best response or the final output. This basically allows the model to sequentially think and improve its answers. The next approach or technique is best of n. And the idea of best of n is very simple. It is saying that we sample n times from the LLM in parallel and then pick the best answer. So from this, we go to something like this. For the same prompt, we sample n different times with n different solutions, basically. And then we have this additional component, let's call it selector. And the selector looks at all these responses for this prompt and picks the best one and shows that to the user. And this becomes the final output. And for the selector, there are different ways we can build it. It can be just a separate machine learning model called reward model to look at all these responses and score them. It can be simpler heuristics like majority voting. For example, in math questions, it can look at different responses and pick whichever response that is more frequently appeared in all these sampled responses. Or it can be any other heuristics. Here is a short example. For this prompt, it's passed to the LLM. We also add this, let's think a step by step, which we saw earlier. And then this LLM, we sample 3 different solutions from it. And we can see the first solution has 29 as the final answer, the second one 28, and the last one 29. So the selector here, let's assume we are using majority voting, would see that majority of responses are believing the correct answer is 29. So it would just pick one of those answers. And in this case, it's picking this one. The last technique we would cover is search against a verifier. And here, basically, the idea is instead of having this setup, we add a search algorithm, and then we rely on the LLM and a verifier to find the best output. So I'll show some examples. First, let's see what is a verifier. A verifier is simply a model trained to score solutions or partial solutions. So whenever we have some sequence of thoughts, we can pass it to the verifier, and get some score. And that score shows that how good this response is for this prompt. This is just a separate machine learning model trained to do that. And the search algorithm relies on it to explore different ideas or different solutions. And search algorithm, they're different, just simply a search algorithm. It can be a best of n, which we saw previously. It could be more advanced searches like beam search, look-ahead search, Monte Carlo tree search, and so on. So here is a more concrete example. Assuming that we have access to a verifier, best of n search algorithm just generates n different responses. And then all these responses goes into a verifier. We get some score. And then best of n picks the best one. Beam search is just making it more advanced and more efficient. So it's passing these partial solutions to the verifier to get the scores at each step. And then depending on the score, it decides to prune or explore certain branches more. And we have look-ahead search, and there are more search algorithms. So this is search against verifier. Before we go to training time techniques, let's see a summary of what we discussed. So a short summary is like this. In a non-reasoning setup, the input directly gets the output. In prompting techniques like chain of thought prompting, which we saw, from the input, we go to a sequence of thoughts, and then we get the final output. When it's combined with best of n, we basically sample multiple solutions in parallel. And then here, depending on our selector, it can be simply majority voting or some verifier. We can pick the best response and use it as the final output. And in search against a verifier, we build this tree, and we use the verifier to explore more promising branches and prune less promising branches until we reach to a state where we feel confident. And in this case, this branch is basically our final solution. Now, let's go to training time techniques. So we already saw that the idea of training time techniques is just to continue training the base LLM to get a reasoning LLM. And there are two main ways to do this. One is supervised fine-tuning. And here, basically, just the idea is to fine-tune this non-reasoning LLM on some chain of thought data. And chain of thought data is basically just pairs of problem, sequence of thoughts, and the final answer. And if we train on this data, this output LLM, the outcome of this would be a reasoning model. And a popular example of this is a star or self-taught reasoner. And basically, they're just explaining how they use the base model to collect COT data in this format, question, rational, answer. And then once we have that, they fine-tune LLM on this data to get a better reasoning model. And they're showing that they're just doing it iteratively. So they keep bootstrapping this model and getting better and better COT data, and consequently getting better and better reasoning LLM. So if you're interested, you can take a look at this paper. So this is supervised fine-tuning. We just basically continue training the LLM. The other technique is reinforcement learning with a verifier. And basically, the idea here is to let this reasoning LLM after SFT stage to practice. So the LLM can generate multiple thoughts for the same prompt. And then we have this verifier, which looks at these responses and score them. And then we use a reinforcement learning algorithm to look at all these different responses and update the parameters of the LLM, such that the LLM becomes more encouraged to generate good answers and discouraged from generating bad answers which verifier believes that are not good. And an interesting paper showing that it works really well is Let's Verify Step by Step, published by OpenAI. So if you're interested to learn more about this, you can read this paper. And for this verifier, we have just typically two types of verifiers. It can be either outcome supervised reward model or ORM, which it scores the entire solution. So it looks at all these intermediate thoughts and the final answer and score it. Or it can be process supervised reward model. where it scores each individual thought separately. So this is very detailed. Again, if you're interested, you can go over this paper. But these are different types of verifiers that we can in practice use. The next technique is self-correction. And the idea here is to train this LLM on a data so that it learns to self-correct itself. So we go from here to something like this after training. So this LLM now would generate some output, then it would self-correct it, and it would self-correct it again. And the key part of doing this is to collect data. And again, we can do supervised fine-tuning or SFT. What we need to do is we need to collect revision data, which is basically a sequence of incorrect answers followed by the correct answer, and then fine-tune the LLM on this revision data. Additionally, we can also do reinforcement learning for self-correction. And a popular example is a score. I think it was published by DeepMind. And it's just using reinforcement algorithm to train the model to self-correct itself. So this is the third technique, self-correction. The fourth technique, which is the most advanced one, is to internalize search. Basically, collect some data and train the LLM on this data so that the LLM knows how to explore different directions and reflect and backtrack and again, generate more solutions and so on. So the key steps here is just the data preparation. So we can use different techniques like Inference-time Techniques to sample different solutions. And then we can, once we have the data, we train. Training is identical to SFT, like identical to COT and normal training. And then after training, we would get this LLM that is able to explore and reflect and backtrack. Popular examples are meta COT or journey learning. And this is just showing that after training a model on this kind of data, the model is able to generate some solutions, and then here it would backtrack and reflect and generate more solutions and so on. So this screenshot is from Meta COT paper. If you want to read in detail, you can go to this paper. And finally, we discussed all different inference time techniques and training time techniques. Now let's see what we know from GPT-5. So when OpenAI released GPT-5, they also released this GPT-5 system card. And it's a very long article. It has 50 pages. And they're sharing a lot of information about it. But most of this information is around evaluation and safety mechanisms and how good the model is. They're not sharing much about the number of parameters or the architecture that they've been using and so on. So what I'm sharing here is what we know from this system card and some other reliable sources. So we know a couple of things from GPT-5. One is that a GPT-5 unified system consists of two models. One is GPT-5 main, it's named GPT-5 main, and the other is GPT-5 thinking. GPT-5 main is more efficient, so it's less expensive, but it's not a reasoning model. GPT-5 thinking is a reasoning model, and it can reason, so it's trained for reasoning. And how it's trained for reasoning, it's not publicly available, it's not known, but it's very likely that they're using one of the techniques that we've already seen to train this model to think. It's probably having an SFT stage, reinforcement learning with some verifier, and internalizing search. So this is the first thing that we know. The second thing we know about this is that there is this fast router that are put right before these models. So whenever there is a prompt, the prompt first goes to this router, and then the router decides which model to use. For example, for certain prompts, we do not need thinking models. The prompt is simply very simple. For example, if we ask like where is a capital of some country, for these kind of questions, it's very likely that GPT-5 main is sufficient. And since it's less likely, less expensive, so it's preferred. So the router decides where the prompt should go. This is the second thing that it's already explained in the system card. And this router is very fast. It's not really costly. The third thing we know from GPT-5 is that they're shifting their focus from hard refusals to safe completions. So what that means is that before GPT-5, the models were using kind of a intent classification on the input prompt to decide whether it's a safe prompt, it's safe to answer this prompt or no. So basically, these models were just using a binary classification of user intent. And then if they, at that stage, if they believe that the input is not safe, it's not, the user is not asking a safe question, they would just simply refuse. Whereas in GPT-5, they're switching the focus on the output. So regardless of whether the input prompt is safe or not, the GPT-5 is optimized so that it can produce answers that are safe. And if you're interested, they have also this detailed paper about these safe completions and this shift. So you can just refer to this. And finally, they have also this thinking pro mode in GPT-5. So what that means is that basically in this mode, they're just enabling test time compute. So it's still the same setup, it's still two models. There is not any additional pro model. But the difference is that now they are using one of the inference-time techniques that we saw, like self-consistency, sequential revision, prompting, and Monte Carlo tree search, and so on, to explore various solutions and various directions to a prompt at the same time. And then they are finally showing the best one to the user. So this is what thinking pro mode means. And just to get a better sense, if I go to ChatGPT, here we have these modes. Instant is basically, if we select instance, it means that we are asking the GPT-5 to use the non-reasoning model. If we select thinking, we are asking the model, regardless of whether our prompt is simple or not, to use the thinking model. And auto means that we rely on that router to decide. And pro is simply we ask the model to enable test time compute and use all those inference time techniques that we discussed. All right, we can conclude the video. We learned what reasoning LLMs are. We explored various inference time and training time techniques to build reasoning LLMs. And we also saw what GPT-5 unified system might look like based on their released system card.